All right. Hi, everybody. I'm Jada from the University of Washington. I want to say thank you to the organizers for putting together this whole conference. Okay. So I feel like I need to justify talking about Venus at an astrobiology conference because Venus is extremely inhospitable, has a surface temperature that's high enough to melt lead. So there's two questions that come to my mind when I think about why Venus is relevant to astrobiologists. One is, what can Venus tell us about Earth? Some people think that measuring the ratio of deuterium to hydrogen in Venus's atmosphere, that Venus once was more Earth-like and maybe have had a lot of water on its surface. But over time, it underwent this runaway greenhouse process and lost its water. People think that in the future, Earth will undergo a similar process and Earth will become Venus-like. So Venus's present state may be Earth's future state. And then the second question is, how can Venus inform exoplanet studies? Exoplanets are something near and dear to my heart. I love exoplanets. So I'm always thinking about that in the back of my mind when I study these planets. I think that Venus-like planets are probably common in the exoplanet population because I imagine it's sort of like Venuses are the end state of Earth-like planets, so they would presumably collect in exoplanet populations as their stars evolve. Secondly, I think that planets with thick photochemical hazes may also be common in the exoplanet population. In our own solar system, of the 4 terrestrial worlds that have substantial atmospheres, so Earth, Mars, Venus, and Titan, 2 of those worlds, Venus and Titan, have thick photochemical hazes. And Earth itself, some authors think, may have had a photochemical haze in its past. So it's interesting to me to try to understand what we can learn about the surface environments of photochemically hazy, enshrouded worlds. I think that has significant implications to future remote sensing and planetary characterization of extrasolar planets. Oh, there's a movie, but it's not playing. Oh well. Pretend the little volcano is going off on Io there. So this is the innermost moon of Jupiter, Io. Io is the most volcanically active body in the solar system because it's on a slightly eccentric orbit near Jupiter, and Jupiter is putting tidal energy into Io and melting its interior, and so Io has these incredibly huge volcanoes like that one spewing off the limb of the planet. A class of worlds proposed by one of my collaborators at the University of Washington, Rory Barnes, has proposed that he thinks that you can get tidal Venuses, which are worlds that have a high enough heat flux driven by tidal heating close to their stars. So these are worlds on slightly eccentric orbits, or worlds that are in the process of tidally circularizing their orbits. And if they have a high enough heat flux, about 300 watts per square meter, you can actually drive those planets into a runaway greenhouse and get what's called a tidal Venus. Roy believes that the danger zone for getting tidal Venuses exists for stars less than about 0.1 solar masses. And that doesn't mean all of those stars necessarily have tidal Venuses. It just means they could have tidal Venuses, depending on the various properties of the planet's orbits and their masses. And the really, really important thing about tidal Venuses is that for stars less than 0.3 solar masses, tidal Venuses can exist within the habitable zones of stars. So they may potentially confuse future characterization missions if we find these planets and don't understand what we're looking at. What this is showing is, I don't want to spend too much time talking about this, but this is showing the planet-star separation angle for various Earth-like, hypothetical Earth-like planets around the nearest stars in the nearest 20 or so parsecs in the Hipparcos catalog. So for the non-astronomers, just to remind you, A dwarfs are the hottest, most massive type of star that I've plotted here, and then M dwarfs that I've plotted are the coolest, least massive type of star. So the planet-star separation for M dwarfs in the habitable zone is going to be less than the planet-star separation for A dwarfs. So these are the stars that are below the MASH threshold, which could host a tidal Venus. And again, this doesn't mean these stars do have tidal Venuses, even if they do have a planet in their habitable zone. It just means that they possibly could. The tidal Venuses could not be detected by the first generation of terrestrial planet finders. That's what these 2 lines are. So those are the inner working angles of the terrestrial planet finders as they were proposed initially. And so all of them are below that threshold, but these planets could be detected if they exist through transit transmission spectroscopy. About 30% of the nearby M dwarfs could host tidal Venuses. Okay, so now my work is seeing through the pale yellow cloud. So how do we actually characterize these worlds? The way you do it is you have to use what's called these night-side spectral windows. They were discovered by Allen and Crawford in 1984. These spectral windows are, you don't want to think of them as literal places on the planet where the clouds are thin and you're actually, peering through holes in the clouds. These are spectral windows, so you want to think of it in wavelength space. So they exist from about 1 to 2.5 microns, at least the ones that I'm interested in. And they're places in the spectrum of the planet where gases are not significantly absorbing. The spectrum is relatively transparent. So you can look in these wavelength regions and you can probe deep down into the atmosphere. And in some cases, for example, the 1 micron window, you can probe all the way down to the surface of the planet. So that's great because this gives us information about the surface conditions of this completely photochemically enshrouded planet. So what we did is we observed them in November and December of 2010 using the APO 3.5 meter telescope, the triple spec instrument, which is a spectrometer with a range from 1 to 2.5 microns and a resolution of about 3,500. These are night side windows because you can't observe them on the day side of the planet, unfortunately, at least in the case of Venus, because in this case, what you're sampling through the windows is thermal emission, which gets completely dwarfed and swamped by reflected sunlight if you try to observe them on the day side. Okay, so just to prove to you that you can see the surface of Venus from Earth, what you do is you measure the 1 micron brightness in each pixel, then you can build up a map of brightness variations, and this little guy here, that's Aphrodite Terra. It's kind of hard to see, but it's darker than the surrounding plains. And the reason why it's darker is because it's higher in elevation. Aphrodite Terra is a highland plateau about the size of South America, and it's about 4 kilometers above the plains. So the adiabatic lapse rate on Venus is about 7 Kelvin per kilometer, so this thing is about 30 Kelvin cooler than the plains. That's why it's darker. If you were to sort of naively try to measure the brightness temperature of Venus by measuring the effective temperature of the cloud deck, you would get a very cold temperature. It's like 218 degrees Kelvin, which is grossly mischaracterizing the surface environment of the planet. So if you were to naively believe that, you would completely misunderstand what's going on here. The actual surface temperature of Venus is about 730 degrees Kelvin. And using, in particular, the 1 micron window again, which is about 96% surface thermal emission, you can measure the surface temperature through the thick atmosphere. You don't need to descend a probe into the atmosphere. You can actually do it remotely. So again, yeah, that measures the surface. And this entire wavelength range from 1 to 1.3 microns, you can measure the lowest scale height. Okay, so the next thing I did is I used the spectra that we collected from the Apache Point Observatory and combined those with radiative transfer models to try to get a handle on the cloud opacity over the planet and also to measure the abundance of minor atmospheric species. So obviously the major atmospheric species for Venus is carbon dioxide, but it has a lot of other gases that are present at much less abundant levels. So one thing I did was I measured the cloud opacity. So these are radiative transfer models where I'm changing the opacity of the lower cloud deck. The relative heights of the spectral windows are very, very sensitive to the opacity of the lower cloud deck. You can see that as you go from, let's see, lower opacity clouds to higher opacity clouds, the windows change heights, absolutely, but they also change heights relative to each other. So you can use that relative effect to quantify the cloud opacity, which is what I did here. So what you're looking at is, this is just to orient you, we're looking at the night side of the planet. Each of these columns is a different night that I observed the planet. It looks like it got a little cut off on here. This one at the very end, let's see, so this is the first night. This is actually the last night, and the very last one is all of the nights co-added on top of each other, just to look for long-term persisting patterns. So the cloud map measures the brightness of the clouds. In the places where it's very bright or red is places where the clouds are thin and you're sampling lower into the hotter atmosphere. And then vice versa, where it's dark or bluer, you're sampling higher in the atmosphere where it's cooler. I measured the cloud opacity using my radiative transfer models here. And you can see that there is a correlation between places where the clouds are thinner and places where you, again, would expect from the cloud maps that it would be thinner. So this row here is built up from the models, and this one is from the data. And there's a good correspondence between what I would expect. It's really important to remove cloud opacity features that are wavelength dependent because those can contaminate your measurements of minor atmospheric species, which was the next thing that I wanted to do. So first I had to use these wavelength dependent cloud opacity maps to remove these features. Another really nice thing about the Venus spectral windows is that they're sensitive to different altitudes. So when you're measuring the abundances of various species, you can actually build up vertically resolved profiles depending on the window that you measure them in. So in the 1.18 micron window, you're sensitive lowest in the atmosphere. And when you get up to the 2.5 micron window, you're probing just below the lower cloud deck. Okay, so I know there's a lot of green on this slide, but these are my water maps. So this is just measuring the water in each pixel across the surface of the planet. Venus's atmosphere is extremely dry. The water vapor abundance is about 30 parts per million. That's a lot less than the Earth has by a lot. And you can see that you get these vertically, so this is from 0 to 16 kilometers, 16 to 30, 30 to 45 kilometers. You can build up what it looks like at different heights in the atmosphere. And then drawing your attention to the, sorry, this should not have been there. These got all screwed up. But drawing your attention to the lower cloud opacity and the 2.3 micron water maps, I did notice that there's some correlations. This one's probably hard to see. But there are some correlations where sometimes thicker cloud regions have less water and thinner cloud regions have more water. This was an effect that has previously been reported by some of the Venus Express team members. And what may be causing this is cloud subsidence, where you have a cloud parcel in the atmosphere that some atmospheric downdraft pulls it lower into the atmosphere. Then the H2SO4 droplets that make up the cloud dissociate into water vapor and SO2. So in some places where you have thinner clouds, that may be places where the cloud subsidence is occurring, and you may be getting thicker water from that because it's producing water vapor. I also measured HCl, hydrogen chloride, which is abundant at about 0.5 parts per million, and CO, which has a really interesting spatial distribution that's previously been reported in the literature by Cotton et al. And what's probably going on here is CO is being produced photochemically from CO2 higher in the atmosphere, and then it downwells at the poles. So you get this higher abundance at the poles. And then by the time it gets to the equatorial region in these kind of circulating cells, it's a lot more depleted because it reacts with other species and becomes other species like OCS. Okay, so takeaway points is, the main point is that completely cloud enshrouded worlds and completely haze enshrouded worlds, even if they're 100% enshrouded, it's not the end of the day for trying to sense their surface environments and characterize what's going on in their surfaces. So I think atmospheric windows are very important because I think hazy planets are probably important in the exoplanet population. Thank you.
So for your cloud opacity, you've been using water clouds there?
So the cloud opacity, I was gonna.
Because there was a model data as well, right?
Yeah, where was my cloud? Sorry. So the clouds are H2SO4 droplets, sulfuric acid droplets, and I'm basing them off of this CRISP 1986 model, and I should have mentioned that these units are in units of the sort of default opacity in the CRISP 1986 model. They're not sort of absolute units, so this is 3 times the CRISP cloud opacity, and this is 0.05 times.
So is the H2SO4 cloud opacity data in that paper, or where do you get the opacity?
The opacity, yeah, I got it from Dave Crisp. He's one of my collaborators.
Okay, thanks.
Yeah.
What is the specific chemical role of the HCl that you measured?
The specific what?
Chemical role of the HCl that you were looking at.
Yeah, so HCl, I'm trying to remember now. HCl has not changed in abundance over the last 40 or however many years that we've measured it. So it's thought to be in equilibrium with the surface. And I cannot remember how they think it's produced. I don't think they think it's volcanically produced like some of the species in the atmosphere. Yeah, I know there is some cloud chemistry between chlorine that you get in the atmosphere and the HCl, but I don't remember.
I didn't understand this tidal Venus stuff, I think. So at Io you have this Laplace resonance with Ganymede and Europa to not get into this tidal locked thing, but how does it work at a Venus surrounding some star?
Right, so Rory would be the person to ask that. But the way it works is you have to assume that the planet's not in a circular orbit, and you have to assume that the time that it takes to tidally circularize is shorter than the time scale for it to undergo this desiccating greenhouse, and that's how you get a tidal Venus. So somehow you have a planet that's either persisting in a sort of slightly elliptical orbit. Perhaps there's another planet in there, just like around Jupiter, that's keeping those moons in an elliptical orbit. Or you have a planet that's being tidally circularized. So it starts in an elliptical orbit when it can be tidally heated, and then it circularizes. So if that occurs in a long enough time frame for it to undergo a desiccating greenhouse, then you can trigger a tidal greenhouse. So these are planets that are close in to low-mass stars. It's directly analogous to the Jupiter system. And you're producing a lot more heat than you are on Io. Io has like 2 watts per square meter, whereas for tidal Venuses, you need 300 watts per square meter. So there's quite a difference, but Rory thinks you can do it.
Thanks very much.